let me finish something for 10 minutes and then pause for questions before I switch gears. So, I hinted yesterday, and maybe many of you know, and possibly this will come up in a big way in the Isidori lectures, the idea that if you have for example, the linear signal model, which is to say a renormalizable theory. This is just the theory of phi. Renormalizable theory of this, just as an example. Forget the Electroweak aspects, just the scalar field theory. You have a nice linear theory like this, and then you discover that there are some light particles and some heavier particle. Then we see that there's a low energy approximation in which you only have these guys. And the exercise I gave you yesterday was to show that the scattering of this, just by itself at low energies compared to the mass of this, looks non-normalizable. In particular, if you characterize it, it is in fact the nonlinear signal model. And the exercise I gave you was to see just that first approximation to it, that the scattering amplitude for these pions looked like E squared over V squared. Okay, it looked like it had a non-normalizable coupling, even though ultimately it derived from a theory which was renormalizable. So we see that this business of taking a renormalizable UV complete theory, this is a redundant, this is this, that at low energies it can look like a non-normalizable effective field theory. Okay? Now, we are right now seeing the standard model, and it looks pretty renormalizable. Let's say that we are operating at low energies compared to tomorrow. Okay? So the standard model looks renormalizable, but there may be some corrections to the Lagrangian that we are insensitive to today, but maybe we'll be sensitive to tomorrow, which are, so it's the effective Lagrangian in the sense of effective field theory, which might be non-normalizable, and they may give us very small effects, but they would be a hint that new physics is around the corner and contributes in this very indirect way at low energies to non-normalizable interaction. So part of the art, that's what I wanted to just end this section with, is what I call precision tests of the standard model. Are first of all useful when the energy of your collider, or whatever apparatus you're using experimentally, the momentum transfers are small compared to the mass of the new physics. Okay? In that case, the right thing to do, the words we usually use are integrate out the heavy particles. We say, this is a pathological way of talking, we integrate out the heavy particles, the heavy fields, and we end up with a theory which is not normalizable, where there can be corrections which are non-normalizable. This is a classic case. We integrated out the Higgs, and we ended up with non-normalizable effective interactions for these pions. Okay. So this basic idea, philosophy, can be used to do precision tests of the standard model. And but it's in particular valid when there's something that, some new physics that is part of some ultimate renormalizable theory, you integrate it out, and you end up with corrections to the standard model, especially corrections that may be, the standard model is already this effective theory only contains, since the new physics is assumed to be heavy, the effective theory only contains the light fields of the standard model. But the interactions, all the renormalizable interactions that you can write down with standard model fields have already been written down. That's what's called a standard model. And all the couplings are measured to some approximation. So the only thing that you could get extra by having new physics around the corner, integrating it out, so it's a little bit heavier than the scale of our colliders, let's say. The only thing you can get are non-normalizable interactions. Okay? Nevertheless, we can try to do experiments. Non-normalizable interactions are typically weak at low energies. Okay, it's just like this. At low energies, at high energies, this is badly behaved. At low energies, it's actually a small effect. So non-normalizable interactions are necessarily weak at low energies, and hence you need precision in order to see their effects. Okay? Now, because you need precision, you would like to have no background from the renormalizable effects of the standard model, the textbook predictions of the standard model. You ideally do not want, you want to see the shifts given by this kind of physics relative to this. And so, in particular, what we look for are approximate symmetries of the standard model. Because if there's an approximate symmetry of the renormalizable standard model, then you have zero background. If you look for violations of that symmetry in nature, it must be telling you something here. Okay? And as soon as you see a non-normalizable effect involving the standard model, then it cannot be extrapolated to high energies. There must be new physics. We're in business, we go look for it with the high energies. Okay? That's the game. So that's one thing. And the other thing is that you look for, so we look for deviations as well as deviations in tree level. Standard model is weakly coupled, so tree level is approximately true. We look at deviations from tree level relations. Of course, tree level relations are corrected by standard model effects, by standard model loops, but since it's weakly coupled, those loops are small, so we also end up with sort of small backgrounds to the deviations that we're looking at. Okay, so this is a particularly sensitive class of things for us to look at. So I just wanted to race through, I don't know, an example of each of my, in each of my favorite class of things. Maybe it exhausts all the interesting things, and think of it that way. But let me just race through to show the diversity of tests that we have for the standard model. We're asking whether there's a gap, okay, to the new physics. And basically, each time we do one of these experiments, we are sort of looking for virtual sensitivity to these scales, okay? These non-normalizable interactions, to make dimensional balance, Lagrangian has to be dimension 4. They're non-normalizable, meaning higher dimension operators that you made out of standard model fields, then the mass scale at the bottom has to go something like powers of the new physics scale, okay? So we're trying to be virtually sensitive to these non-normal, to the new physics before we make a plan for how to get explicitly sensitive to them. Okay, so let's start. Here's a famous tree level relation. The gyromagnetic ratio of, say, the electron or the muon at tree level, just by studying the Dirac equation, forget second quantization. This is the answer. Okay? So therefore, this is a deviation from the tree level relation, and it could be either the electron or the muon, or these are the best tested things. They're the pointiest particles that we have. Now, if you do your classic QED course, you'll see that there are the typical diagram that corrects this are diagrams that look like this in QED. And so you actually do have tree level relations. They are corrected already in the standard model, but you could look, but there might be, so you can look, you can calculate these and work to higher order, but you could also have new physics contributions to such processes. This is still the photon or the electromagnetic field. But this, I can replace this internal virtual photon by some sort of new physics coming in, okay? And the experiments for magnetic moments are, of course, done at very low momentum transfers. So this new physics particle is highly off-shell. It's a very virtual test. Nevertheless, you have incredible sensitivity in these experiments, and so you might be sensitive to this. Now, should you, case by case, well, this new physics, it could be a Z prime, it could be some second type of Higgs. We could characterize all the different possibilities. And in each case, you can calculate it. You can add it to the standard model prediction for this, and then you can do the measurement, and you can get some bounds, and so on and so on. Should you do it that way? No. Because whenever you do a virtual test for new physics, you're doing something very inclusive. Many different things, many different types of new physics could give you a deviation here. So the art of effective field theory in probing for new physics is to say, this thing, if I actually do an example where I take, say, some particle, put it here, do loop level, this is what's called tree level match. The exercise I gave you was all at tree level. That's called tree level matching to this non-normalizable effective theory. Here I'm being forced to do loop level matching, and it can be done, and this is the art that you must learn, and hopefully in the Isidori lectures you will have more discussion of things like that. But this is loop level matching to an effective theory, and the effective operator is of the form, so these magnetic moment type effects flip the chirality of the lepton, and so they look like this. Electron right, the most sensitive particle for heavy physics, the gambling odds are muons, so I need to put muon there. So left-handed, right-handed, there's a flip, and if you're writing down an effective Lagrangian of for the standard model, to have electroweak symmetry, you have to have the Higgs. When you do these experiments, you're only probing this part of the Higgs. But since we know gauge invariance has to be there, we might as well say that this is the operator that we're probing, and sorry, here's the photon. Okay, in the non-relativistic approximation where you're probing these leptons, the sigma dot F becomes sigma dot B, the non-relativistic magnetic moment interaction with an external magnetic field. Okay? So there's some coefficient that comes from doing this calculation, and then, or if you want, you can trade it because this is dimension 6. There's some effective scale that shows up here. So this is a contribution to my L effective or the standard model. My standard model is only an effective field theory, the remnant of some more complete theory. And so it doesn't just have normalizable terms, it can have these non-normalizable terms. And we can experimentally put bounds on this coefficient, or if you want, we bound this. And it covers all these cases. In one shot, we cover all these cases. And if we are so lucky as to see a deviation, and you may know that there is at least a mildly controversial deviation in the G-2 of the muon. I would say controversial, not mild. Controversial deviation. There's an anomaly in an experimental deviation in this thing, as best we can understand theory, because you do need to do all of the standard model corrections at high enough order. These involve the strong interactions. So this is a beautiful technique, a way of thinking. You have to hardwire it into your head for thinking like this efficiently, rather than working out 100 examples. Once we see a deviation, then we can try other experiments and try to figure out exactly which type of particle it is, and so on and so on. But that can wait. Let's first make a discovery beyond the standard model efficiently, and that means you have to adopt this language when you're doing this kind of experiment, when you're probing for new physics using precision. Okay, so that's the philosophy. There is what are called Electroweak precision tests. There's a huge body of things. The general idea is that the standard model has these as the Electroweak parameters. Okay, we've talked about a number of precision things already. We've already talked about the Higgs boson and how they are trying to measure its different properties that come from using the standard model Feynman rules and looking for deviations. The rate to photons, the rate to multi-leptons, the ratio of those. So I've already discussed a number of precision tests very fleetingly, but I have proton decay. So just for variety, here's another one. I'm not even putting the parameters of the Higgs boson, so I'm not even putting that in. But these are the classic parameters in the standard model that are the inputs, and usually we measure these by simply measuring the 3 best known experimental quantities of the Electroweak sector, okay, and G Fermi, as say measured in muon decay. Very clean process, right? And so now that you have these parameters, you can predict everything else. Okay. So one of the things you can predict is, say, the W mass, which of course at tree level, so we're again looking at some tree level relation here. The tree level relation, but here I'm pointing to something different. Okay, say it like this. The tree level relation looks like this. Of course, the mass of the Z at tree level looks like this. And I want to simplify the discussion, so you can put the following thing back. But let me take G prime to 0, which is easier to do in your head than an experiment. But anyway, let me do that. And just say, look, there's something remarkable. There's something remarkable. If you just forget this irritating thing called hypercharge, the mass of the Z is the mass of the W. Okay? And that's, remember when I started my very first example of non-abelian massive gauge theory, I happened to start with a theory which has all the massive spin 1 particles being degenerate, like this. Okay? Now, I didn't do that for no reason. It's because the world happens to live in that approximation. And remember, the symmetry that arranges this for you, that maintains this, despite the fact that we've broken Electroweak symmetry, we are retaining, as an approximate symmetry, this SU2 custodial. We're breaking Electroweak SO4 down to Electroweak SO3, which rotates these 3 states among each other. Okay, and this is an approximately true fact. Okay, deviations from this, well, I'll give you the effective operator in a second. Now, when we test this relation, and many others in the same class, when we test this approximate symmetry of the standard model, it is a probe for new physics again. We're not doing it for fun, we're doing it to probe for new physics. Let's see what kind of example we could have of new physics. So consider a new physics model where in the UV, I'm adding some heavy particle and it has the following form. Under SU2 left cross SU2 right, it is a 3,1. It doesn't transform under SU2 right, but it is a triplet of SU2 left. Okay, just like the W boson is a triplet, it's a triplet of SU2. Okay, and but it's very heavy. There. This is the correct sign mass. This is not tachyonic, right? This is just the regular mass channel. Okay, but I'm going to couple it. I'm going to couple it to the standard model Higgs. So I'm going to use 2 Higgs multiplets to make a triplet, composite operator which is a triplet, and then contract it like this. Okay. So here is a potential. In fact, this potential is SU2 right. It preserves SU2 left. It's better. That's a gauge symmetry. But this thing is being violated. I've broken SU2 right. Again, we can put the hypercharge back, but I don't want to waste time. So.
Okay, so remember that it's a special feature of the purely standard model Higgs doublet theory that the potential of the Higgs doublet theory is that once you write a potential that preserves electroweak gauge symmetry, it is automatically or accidentally got custodial isospin as well. So you only insist on this for the Higgs potential, but there's nothing renormalizable that you can write down which is not also got this at the renormalizable level. Now we see we can write down something which does violate this. Okay. And it's easy to see what this theory will do. In a sense, you can see at low energies what the theory wants to do. It, in isolation, this triplet theory will have, in isolation, TA would like to be 0. Okay? It's just a massive scalar. 0 beta. But when electroweak symmetry breaks in the standard Higgs sector, it gives a kind of kick to this potential. So you can see it. Here is the potential. Here's the potential for T. And then because I add this extra term with kappa in it, okay, this is the mass term, and I add the kappa, it somehow it shifts it like this, and you end up with some vacuum expectation value for the T. Okay. And in fact, that is it. By the way, the shift is once I look at low energies and I replace the Higgs by the Bev, okay, which is 0V, 0V. So at low energies, you can replace it by the Bev. Then this term becomes linear in T. The linear in T thing shifts and pushes you off like this, and you end up with a Bev for T. But when you have a Bev for T, then you'll have new contributions to the W boson mass coming from this. And you can see what it is because the d mu TA contains epsilon. This is the gauge covariant derivative. Now looks like this. And in fact, if you're careful here, the 0V's, and you keep track of this Pauli matrix, you can see this is giving only something in the diagonal direction of tau. So it's not tau 1 and tau 2, it's tau 3. So this is really tau 3, T3. T3 is the thing that gets the Bev. Okay. So if this is T3, and this is the epsilon, then this can only, so if I put the Bev here, this can only be W1 and W2. So in fact, at low energies, this thing contributes a mass to W1 and W2, or if you want the plus W plus minus. It does that, but W's Z being the third component of W in the hypercharge goes to zero limit. This is 0. Okay? So if you work through this example, you quickly see that there is a deviation from the standard relation. And if you go measure the W mass, then you're starting to set bounds on this mass, the mass of the new physics. Okay? Now again, should you go around thinking of every theory that does this, unless you happen to love one particular theory, which is fine, sometimes that's the mode that we're in. But if you are a person doing these experiments who would like an efficient language to talk about all theories that violate custodial isospin, and indeed, there is an effective operator, and you can, this is a tree level example that I'm doing here, you can pretty much see what it is. I should replace this T at low energies, a good approximation to T is to just solve this equation, is to minimize this potential. Okay? because kinetic energy is a small effect. When the mass of T, at low energies, the mass is much more important than the kinetic term. So at low energies, we can say that TA at low energies is approximately kappa H dagger tau A H over m squared. Okay. And then that's the leading thing. But now I can, since this is where the W boson masses are coming from, even if it's subdominant, it's the leading place. This is subdominant to this, because the mass term is so big. But even though it's subdominant, this is the leading place where these W boson masses are getting shifted. So let me plug the solution for T got from here and plug it back into here, okay? And that, so, and let me put effective. And you get this effective operator. Beautifully standard model invariant operator that looks like, has this form for some kappa, lambda is like kappa squared over m to the fourth is lambda squared, and the dimensions, I'll figure it out, you can do it, okay? It's easy. So this is an effective operator. The coefficient of this operator can be measured, can be tested by testing all of these relations, like what is the W mass and so on. The coefficient in various normalizations is called the T parameter, the rho parameter. What is it called here in Europe? In the Barbieri school, epsilon 1. So it has many names. You can name it after yourself too. And but here's an effective operator, very famous. And you see, it involves only standard model fields. Its distinction is, it's higher dimension. It's not a normalizable. It's not that it's not standard model, it's just not a normalizable. But if we see the effects of this, then immediately we know that somewhere above us there must be some new physics. Okay? That's the beauty of it. And the other beauty of it is, it violates a symmetry that the renormalizable theory has to very good approximation. And so we are able to see more clearly when there is a deviation. Okay, we have great sensitivity. Okay, and I think the last one is only to say, of course, you're going to have an entire lecture course on flavor-changing neutral currents. And so, you can have things like this, new physics. New physics, unlike the standard model, which has a very good approximation in which the exchange, if you have neutral pairs, or let me say it like this, if you have neutral pairs of quarks, so the pairs, the Q bar Q pair is neutral, say, the interactions of this pair, the transitions of that pair in the standard model are mediated by things like Higgs exchange or Z exchange, and are very flavor symmetrical. They conserve flavor symmetries, which are an approximate symmetry, therefore, in these processes. And therefore, we look for new physics exchanges which violate the flavor. You have S bar D coming in, and out comes S D bar, D bar S. So these flavor-changing things, again, if we dress it up with gluon, if we have access to these states, they're kaons. And we can look for KK bar mixing and so on. So I'm stopping on that just to say that this is a very important probe, and flavor symmetry is so well preserved by the standard model, experimentally speaking, by the Jim mechanism of the standard model, that the background, if you like, to seeing the new physics is very small, and we have incredible sensitivity. We have sensitivity to mass scales here, which are, for example, in this kind of a process,
for order 1 couplings here, and violating flavor symmetry maximally, we have sensitivity up to, so we have bounds that say this is bigger than things like 10 to the 5th. Wait a second, 10 to the 5th GT. Ridiculously high number. So each time we do one of these experiments, we are shooting a bullet into the roof, trying to shoot the burglar on our house. And we're waiting to see some blood drop down to the ground. And nothing has happened yet. So we're starting to wonder, is there somebody up there or not? And this bullet goes very far. By the way, I should just say that the last one that I had in mind was, again, just like the magnetic moment story, but if there's CP violation in the new physics, then it can give rise to a very powerful class of effective operators, which are just like the magnetic moment ones. Also have quarks. But the CP violation shows up in hooking together the sigma matrix and the electromagnetic field using an epsilon tensor. In which case, at low energies, instead of being sigma.v, spin.v, it becomes spin.electric field. And so these are the electric dipole moments. Okay. And so it's very powerful experiments and very sensitive experiments, therefore, that can probe these. And this is one of the tightest, in my view, one of the tightest set of constraints we have. Not because it probes scales as high as this, but because it does it even in physics which has special flavor structure that avoids these kinds of problems. CP violation is an independent test. And CP violation appears when there are phases in the couplings of your beyond the standard model theory, and these are, in some sense, rather typical and to be expected. Then they can feed into these EDMs. And so these constraints are very powerful. Okay, so there's my favorite list of important classes. Each is just an example. That's not the entire list. The list is vast. But each is one element of a class, and that is my list of all classes that I more or less keep my eye on. Okay, so now, here we go. I want to switch gears. Now, why is this not totally discouraging? Because boom, 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 we've been shooting it. Nothing is dripping down to us. Because case by case, we have got examples of rather beautiful theories in many ways, which evade all of these things. Just like the standard model has reasons for having a gym mechanism, you can have other theories beyond the standard model which contain within themselves a generalization of the gym mechanism and evade this. Okay? They may not evade it as perfectly as the standard model, or maybe they do, and so on. So it's not conclusive. Similarly with these EDMs, there are examples of theories that easily evade them. And the same with all of these things. And so the question is, who evades all of them? And that's a tough thing, and it depends on the standards of your theorist and how beautiful the theory is, and so on and so on. So these are the cause, everything I'm saying here is the cause of grave concern that we are probing up, and if you expect physics at the TeV scale, that it should have shown up somewhere, but we don't have a proof that it should have shown up in one of these tests. It's something you have to feel out. Until, if you want to be a beyond the standard model hunter, even if that means that you're doing standard model calculations, okay, even if you're calculating backgrounds or whatever, but if you are psychologically training yourself for going beyond the standard model in some, or helping to go beyond the standard model in any way, you must weigh this data. In some way, you have to have some compactification of this data that you look at and think about and go to these lectures and so on. And weigh what is the possibility of going beyond the standard model in explicit experiments where you are really trying to do this, okay? Like the LHC. So, this is a concern. What is going on? What is going on?
But there seem to be so many loopholes that it is not, as I said, it's not a situation where you say, we already have checked, there's no point running the LHC. Far from that. But whatever this new physics is that we're looking for should have some special properties. That is totally clear. And it can. We have a lot of examples, and what is not clear is how smart humans are, which is, we found some examples. Each of them has some flaw that you can point to, but the flaws vary. It's not the same flaw over and over again. So, does nature have another story which is similar, but in detail it's different, and in detail it relates to these things in different ways. Okay, so I want to switch for a second. First, magic here. Okay, so we all know the Mexican hat potential. This is what we've been studying here in some way. Okay, so here's the Mexican hat. Sorry. Here's the Mexican hat. I want to switch to something which I'm going to call the Indian hat. Because you often see people in India holding up a basket like this. Okay. So I want to discuss, if you look at the standard model, these aliens, when they look at the standard model, they don't love it as much as us. They look at sort of the general features. It's the standard model chiral gauge theory structure. There are n generations. Then there are these classic parameters, lambda, the fact that this is negative, all that kind of stuff. So what I want to do is to switch and say this is 3. I'm going to do the 1 generation case for simplicity. And I'm going to take mh squared to be positive. Okay? In fact, we keep saying that there's nothing in the standard model that stops the Higgs mass squared, whether it's positive or negative. It could be very, very big. Okay, so here's the Planck scale. Let's say this is the Higgs mass. Incredibly big. And so we're trying to figure out what's going to happen to all of these massive particles. They've got their mass through electroweak symmetry breaking. Okay. Naively, we should just say, forget about this. Okay, so let's just do that. Okay, so now let's look at the QCD subsector of this theory that we have. We don't have any electroweak breaking to talk about, but let's go to the QCD subsector. And in the 1 generation theory, so let's just throw away the Higgs. In the 1 generation theory, QCD has this simple form: U bar IB slash U plus B bar IB slash B minus quarter D union squared. And remarkably, this has global symmetry. And the global symmetry is SU2 left cross SU2 right. And this is the thing that rotates the U and D, the left-handed chirality of U and D, and this rotates the U and D right-handed chirality. Okay? They are what you would call chiral isospin. Okay? And you don't talk about chiral isospin to experimentalists. They don't go around seeing all the different degeneracies associated with chiral isospin. And that's because it is spontaneously broken by strong interactions. It's broken strongly by the strong interactions. And all you end up is with is usual isospin. And isospin would be exact if this was the only physics in the theory. So, and it would be approximately true even in this thing. Okay, so let's pretend that our aliens come from a different universe, and this is the universe they come from. And one can wonder, there's no electroweak symmetry breaking, there are no masses for the electron, where are the atoms then? What are these creatures made of? But, so, they're telling you the story. In our universe, this is what happens. And so we already have this classic form of symmetry breaking sitting inside the strong interactions, and it happens seemingly innocently enough because the coupling at very high energies, QCD coupling, starts off very weak. At very high energies, it's weak. The renormalization group, as you know, gives rise to asymptotic freedom. It gets weaker in the UV, but in the ultraviolet it gets strong. And then at about the GeV scale, or several hundred MeV scale, it gets so strong that magical things start to happen, and you get confinement. Okay, you form in large number of bound states, protons, delta resonance, etc. But this is one of the things that also happens at that scale of order GeV. Okay. I'm being sloppy about the numbers because it's their universe. We are about as interested in them as they are in us. Okay, so in fact we can characterize it. There is the order parameter of the symmetry breaking, which is no longer a single scalar field that sits here, but it is a scalar bilinear composite operator that now gets a Bev. Okay, in this world. And you can see that this thing that has a non-zero vacuum expectation value transforms under SU2 left and under SU2 right, and so it actually violates. This thing is breaking SU2 left, it's also breaking SU2 right, but for this equality, this combination is actually preserving SU2 isospin. Okay, check it out. So we indeed have this wonderful breaking here that we spend so much time on. And indeed, this thing is got this is gauged in the real theory, so in the full theory that I'm pointing to, the entire standard model of one generation. This is gauged by SU2 Electroweak, and this thing is partially gauged by U1 vector. Okay, the diagonal generator. So in fact, this is implying Electroweak symmetry break. Okay. And this kind of breaking by non-perturbative physics is usually called dynamical symmetry breaking. Usually DSP. Okay. And so, by the Higgs mechanism, it implies masses for the W and the Z, satisfying the approximate custodial symmetry relations, so they're approximately equal. And it's of order G times GeV. So, G electroweak. So it's of course, it is smaller than in our world. So it's different in that sense. And of course, the Goldstone bosons of this are nothing but the pi plus and minus and pi zero of nuclear physics, as you well know, are the Goldstones that are eaten. But now they're, instead of being in the spectrum, they have eaten the pi plus minus and pi zero. So these degrees of freedom are the fictitious objects of the Stuckelberg trick.
that we discussed earlier, they're no longer present in the spectrum because of the Higgs mechanism. Now, what's remarkable here is that rather than giving formal definitions of what is naturalness, and hence the opposite of naturalness, which is the hierarchy problem, we can appreciate something that worked out in this case, okay? Which is, we just use the chiral gauge theory structure here, and it just automatically is forcing this relation. But we can ask why, so remember, the aliens are asking themselves, just keep it simple, why the spectrum looks like this. Is there something special about the lightest particles that we see? So I haven't talked about the fermions yet. Let me just stick to this. They're asking, why is the spectrum light? And then they see this carefully arranged chiral gauge theory structure, and that tells them at least why all the particles can only get mass after electroweak symmetry breaking. But what it doesn't tell them in the standard model is, why is electroweak symmetry breaking happening at low scales? It could have happened way up here. Whereas dynamical symmetry breaking offers a 90% answer to this question. Because the renormalization evolution that we're pointing to here, you can actually understand in what sense that spontaneous symmetry breaking like this happening at a low scale. In what sense is this low scale naturally, automatically, something that can be very, very small compared to the Planck scale? So let's go way up to the Planck scale and start the story. The input parameters at the Planck scale, where the standard model emerges as an effective theory, would be alpha QCD at M Planck. Okay, so at the Planck scale, this is my input QCD coupling. You can ask parametrically, what is GeV? When I say GeV, what is it? If I vary alpha at the Planck scale, my input parameter, if I vary it, what is this? And it is a famous fact that you should learn, that the renormalization group invariant quantity that can, like this is the notion of dimensional transmutation, that the renormalization group invariant quantity that can set any mass scale that emerges through confinement, such as the mass of the proton, or the scale that I'm calling GeV, which is this breaking scale of this symmetry. Any scale, the QCD Lagrangian here has no explicit mass scales. But because of the need of the renormalizable theory to introduce a renormalization group scale, secretly a mass scale emerges. The emergent mass scale has to have the form which looks like this. I was hoping I would remember off the top of my head. We can easily work out what the exact formula is in terms of the beta function. It's given by the beta function. But a good approximation is something like this. So this is kind of a crude approximation to the renormalization group invariant form of any emergent mass scale that becomes physical from a theory with one coupling and asymptotic freedom. It has to be of this form, and there are corrections to this, but they're subleading, as long as this is small. And so if I put in M Planck, our aliens can now ask the question, why is this scale so much smaller than this scale? And they can see that it requires only a very mild, it requires only a very mild smallness of alpha. If alpha is just a little bit smaller than 2 pi at the Planck scale,
I end up exponentiating the result and I get an incredibly small scale for hadronic physics in the infrared. Okay, so now you could say alpha could have been 2 pi, in which case lambda QCD would be M Planck. You could say that, except it requires, it's no longer such an incredible coincidence that the hadronic scale, and therefore the W mass, is small compared to the Planck scale. It requires only the mildest accident, which is that alpha should be, which could have been any order 1 number, should be, say, 1, or in this case, maybe 1/5. Okay? Sorry, 1/30. That mild coincidence that alpha is a little bit small is enough to say why you get this enormous exponential hierarchy. Okay. So this is what we will call we see it, it's part of the standard model already, except in a different part of the parameter space. We already see something that we would find incredibly satisfying to understand the tight chiral gauge theory structure brings the seeds of electroweak symmetry breaking with it, and the scale of electroweak symmetry breaking is an emergent scale in this slow, creeping renormalization group sense, rather than some scale that we directly put, you directly put it into the Lagrangian, and as the Planck scale, whoever is putting it in the Lagrangian at the Planck scale said, I want it to be 10 to the minus 15 in terms of Planck units. Okay, that's different. So this is what we call perfect satisfaction for a while. And indeed, the aliens are surprised because this is the way it works in their world. And they've been very satisfied for a long time, and it's puzzling what's happening in our world. But you might still say, well, I still don't understand why there are any atoms. Because, yes, this is a wonderful world. The W boson mass is there. Is there a Higgs boson of some sort? And because our world seems to have it. Well, it seems that it's a matter of detail. What is a Higgs boson to the experimentalist? You can think of the Higgs boson. Again, Higgs boson is something that could decay. If you look at the linear sigma model, you can have this kind of process. So if you want, look at pi-pi scattering, and you're looking for some, bump, and you say, that's the Higgs boson. Okay. Let's take the operational definition. So you can ask, really, what about these guys? Do they have the Higgs boson? Well, since we know this theory, at least the QCD part is very similar to the QCD of our world, we know that roughly the answer is, yeah, they have something. It's called a sigma resonance. It's part of the, roughly speaking, what is this actually a bump? It's not quite clear. But in the same quantum numbers as the Higgs particle is this, in this theory, there is something called the sigma resonance. And the difference is, while in our world, the mass of the Higgs is quite approximately the mass of the Z. Okay? 1.5 times the mass of the Z. In this world, the mass of the sigma is closer to, in fact, if you actually, I'm being sloppy about the exact putting in there, but you find that the mass of the sigma would be several times the mass of the W. While the mass of the Higgs in our world, partly because it's so degenerate with the W and the Z, has a very hard time decaying. So that the width of the Higgs is whatever, 4 MeV, it's some ridiculously small number. But to some extent, not because it has weak couplings, but because it has so few available, of the strong couplings it has so few available decay modes. In this world, because this thing is actually heavier than the W, it can decay very easily, and it's much broader. Okay. Details. Okay, so I just want to say, yes, there's something like a Higgs boson in this world.
if this is a moral tale, like all tales, if this is a moral tale, maybe something like this is going on. It's not exactly this, because there's a sharp distinction here. Maybe it's not exactly this, but something like this, and maybe in some slightly different strongly interacting theory that gives the W boson a mass. Not real QCD, but some replica of QCD, or something which is not quite a replica of QCD, only crudely. Maybe the sigma resonance is lighter. Okay? So, this theory looks in that sense a little bit like ours. But we're missing this fact that another role of the Higgs boson is that it also gives mass to the fermions. Now in this world we're lucky because the proton gets mass through this process. So proton, neutron, they're all heavy. In fact, in the spectrum, if I zoom in a little bit, here's the mass of the sigma, here's the mass of the proton, neutron, and this interesting spectrum keeps going. And here's the mass of the W, nearly an order of magnitude smaller. Okay. This is almost done to scale. Okay. In our world, you got to the mass of the Higgs, and we don't see anybody else in the near vicinity of the Higgs mass. Unless it's incredibly elusive, but these are strongly interacting particles, so we don't see anybody near the mass of the Higgs in our world. In fact, given all the evidence, we're starting to think that there may be a gap, a significant gap, before we see things. So it's looking a little bit different. But you never know, maybe small differences play an important role. There may be a different version of the story in our world that is playing out, where the sigma is, or the Higgs boson is actually much lighter than the typical scale of other hadrons, okay? This sigma resonance is a composite. So if you think of it as, in this theory, playing the role of the Higgs, this is a composite Higgs, okay? The secret of why electroweak symmetry breaking happens far below the Planck scale is answered in this story. And the price you pay is that the would-be Higgs boson is a composite. Okay? And the things that are eaten by the WMC are composites, not elementary particles as posited by the standard model. Okay? So we have to have some differences with the exact story that I'm telling. But perhaps the biggest problem that we're facing right now is we have nuclei in this world. We have nuclei because we have the proton, at least we have the simplest nucleus, which is the hydrogen atom. We have protons. That's good. But to get atoms, we would like the electron to be orbiting around it, which requires the electron to have a mass. And so far, I've said nothing that would give the electron a mass, because the electron is not a participant of all this strong dynamics. And so we can ask, how does the electron get a mass? And our friends from this other universe are obliging. They say, you know what? In our world, somewhere up there, there is granification. Let's see what that does. You see, in granification, the effective operator, when you integrate out the heavy granulified gauge bosons, the so-called X and Y gauge bosons, which are way up there in the gut scale, you end up with effective operators. So, at the gut scale, so below the gut scale, you can forget about guts, you can match to a theory which is non-renormalizable, containing proton decay operators. Okay, so they look like things like Q, 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 L, where everybody is left-handed, over m gut squared, which really means the mass of some x boson or y boson. There are other things, for example, that look like Q, U right, E right, and so on. Okay, there's left-handed things, right-handed things, but they're all of the form proton, something that you can think of as creating a proton, 3 quarks, and lepton. And I gave you an example of diagram earlier that gives you these kinds of things. So, it's not surprising that there are these kinds of operators. Now this is a very interesting guide, because if you imagine let's start with a positron. Here it is. This is a point particle. Okay? The proton is a composite particle. This is a point-like particle, suppose in this theory. And then you evolve this in time. So you act with the Hamiltonian, and the point particle stays a point particle. But occasionally, in the Hamiltonian, you have this way down at low energies. We're operating down here somewhere. But occasionally, you have to act with the perturbation to the Hamiltonian, which is this term here. And when that happens, you end up getting this. So you evolve regular evolution, point particle, point particle, point particle. Occasionally, rarely in the Hamiltonian, this happens in perturbation theory. This thing acts, and this thing is, so this thing destroys positrons, right? Creates electrons and destroys positrons. And so it gives you this. Okay. It destroys the positron and you get the vacuum there. And then this thing can give you a proton over m squared plus maybe some excited protons, excited baryons. Okay? So that means there are oscillations. Or if you like, the mass eigenstates of the theory are not purely, naively would say, I know there are different types of fermionic mass eigenstates in my theory. There are point-like mass eigenstates with charge 1, and there are composite mass eigenstates with charge 1. Charge 1. But actually, because of the action of these effective operators, the mass eigenstates are mixed up, just like in any oscillation phenomenon. And in fact, the mass eigenstates are neither purely point-like nor composite. Okay? So this is what is called a partially composite particle. So you want diagrammatically, the positron that you see in experiment in the world of our alien friends is equal to the elementary particle called the positron, if you want, the textbook object that you think is point-like, truly point-like, plus some mixing angle, which we'll see in a second has got to be small. But well, we can see it later. When you do this, this thing is going to have some, you have to figure out, obviously, this matrix element to produce protons is something like this. So that the mixing angles are small. Let me just call them proton. And so this is the textbook proton, which is an absolutely 100% composite particle. And then you could have the excited proton, the excited baryon. I'm going to be sloppy about all this, but basically you have some mixing going on. Where this epsilon is
got to be suppressed by the gut scale. Diagrammatically, you can draw it like this. The pure, in perturbation theory, the pure lepton mixes, as it propagates, it mixes with the pure proton and mixes back and keeps going. And so it's oscillating along. But the proton experiences chiral symmetry breaking maximally. Okay? Whatever Higgs mechanism is, or just spontaneous symmetry breaking is occurring in the QCD sector, this guy feels it big time. Okay? The maelstrom of the proton mixes the chiralities left-handed, right-handed. Okay? This is a Dirac particle. So it means that passing through this, there is mixing of the chiralities of left and right. And so the electron gets a mass. Okay. And did I have a number for the mass of the electron? Yeah, you can see what it is. The mass of the electron should therefore be some epsilon. Now you can see in detail, there are sort of, in detail, you might say it's a small effect. There is some operator that's relevant for the left-handed chirality, there's some operator that's relevant for the right-handed chirality that we're talking about. And so there'll be sort of an epsilon left and an epsilon right. Okay. So you'd say it's epsilon left, epsilon right. And then the going rate would be the mass of the proton. And so if you work it all out, given this relation here, you'd say this is lambda QCD to the fifth m gut squared. N gut to the fourth. Needless to say, this is much, much, much smaller than the mass of the proton. But good news qualitatively, because it says that the electron should be light compared to the proton. But this is so ridiculously light that indeed there are atoms in this world. Now you know how big our aliens really are. They're very big creatures because their atoms are so big. The electron is so light, the orbits. If you like, the size of an atom is 1 over alpha. This is the standard formula for the size of an atom, the height of an atom. And now, of course, it's very, very big. So that's okay, qualitatively. Now you understand why they're aliens. You can't understand them very well. It's almost like Americans. This is not going online. Very good. So it's an interesting world. That's why they live, etc., etc. But this idea of partial compositeness seems really pathetic, because in the real world, the mass of let me just connect to the real world. Our aliens, having come from this environment, have a rather simple guess as to what's going on in the real world. Strong dynamics are very, we know so much about this story of the aliens simply because the central engine of everything here is QCD, and we have so much data that we can work it out. Other kinds of strong theories, we have less data, and because they're strongly coupled, we cannot work it out easily analytically. But we have to ask whether this blind spot is still a place where the real world lies. Okay, the moral that I told you is in fact the moral for the real world. Of course, QCD pions are there in the spectrum. They are not the guys that are being eaten up by the real W and Z in our world. So it's presumably there's some new strong sector with dynamical symmetry breaking whose pions are eaten by the W and Z. The original proposal was a replica of QCD, because then you could calculate by just using the numbers from QCD. And instead of getting masses of order GeV for the W boson, to get masses of order 100 GeV, 100 GeV, you just said that Technicolor was a stronger version, or the lambda QCD of Technicolor was just bigger than the lambda QCD of QCD. That's the original proposal. Now we have other things we better consider, although there were already reasons to consider it long ago, which is the fact that we know there's a Higgs boson, and the Higgs boson is not several times the mass of the W. The real world Higgs boson is only comparable to the mass of the W. But these are the kinds of things, for the moment, I want to say, these are the kinds of things which some slightly different strong dynamics could make sense of those kinds of details. So the word Technicolor is important because it can be used like this. Technicolor or Technicolor with a small t. And it causes endless confusion. Okay? It's like Xerox and Xeroxing, even if I'm not using a brand name Xerox or something. So I'm using it like this. Something like Technicolor is saying it's something like Technicolor because it's based on strong dynamics, something like QCD, impressionistically like QCD. Many people say, Technicolor is ruled out. This is what they mean. A carbon copy of Technicolor translated into the real world. I mean, a carbon copy of QCD taken as the model for the Higgs sector would not have the light Higgs like the one we've just seen, and there are many other issues, but essentially that one, that's the easy one. And so it's ruled out. But what we really mean is something like this. And it's amazing what brilliant people, therefore with an agenda, mistake this for this. Okay? Because in this, the details matter because you can work them all out. In this, we are substantially in the dark. I want to introduce some tools, but this is, we don't know whether this is alive or dead. And we have to be a little bit lenient to the thing that we understand least, which is strong dynamics. So that's the plan, but we got a problem, which is that this plot that I just told you here seems to be giving you ridiculously small fermion masses. And you see, even ordinary quarks are like leptons to this Technicolor. Okay? Leptons are, to my analog story of strong dynamics, what quarks and leptons are to Technicolor. They are not charged under Technicolor gluons. There are some other quarks. We have to introduce some new quarks, techniquarks, that are charged under Technicolor. But in the real world, the mass at the top is comparable to the mass of the W. It seems like, in terms of generating fermion masses, fermions that you think are elementary, you can only, even the mass at the bottom is an order of magnitude lighter than the mass of the W. Whereas this seems to be a way of getting masses that are ridiculously small for fermions. Okay. And so there's one new idea that is possible in the strong dynamics game, which is a big break from the way QCD behaves. Not a small, some detail, the sigma resonance is light, the sigma resonance is heavy. Some big break with the way strong dynamics works. And it is a hypothesis that you can say. And that's just watching the way the prediction works here in terms of calculating this, this mixing angle. The way it works is that you start at the gut scale, you match, and you generate for lower energies than the gut scale effective operators that look like this. And then you have to do renormalization loop for the coefficients of these. So let me not call it that, let me call it G prime,
left, right. And just like all couplings, you have to do a normalization group and run it down. And you run it down to the scale at which the next interesting thing happens, namely confinement, proton, da 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 da. Okay, so you have to run it down to something of order the lambda QCD. Or in the real world, it would have 10. Now this running, sort of the, so again, this is the kind of thing that's very important to do when you integrate out the W boson mass and you run flavor violating operators from the W boson mass to the hadronic scale where we do experiments. This is exactly the kind of running that you have to do. And I'll just give you, so you'll probably hear a little bit more about it in detail. Instead, I will give you the kind of impressionistic thing that happens, which is you end up with the original thing, and then you end up, the running effects can be solved. You can solve the renormalization group if it's not too many different couplings. You can solve it approximately. And you get things that look like this. The lambda QCD, MGUT. So this is the impressionistic version. Alpha strong, U. Okay, you end up with things that look like this. By solving the renormalization. Not crazy. These kinds of effects are called anomalous, the effects of anomalous dimension. So just like mass terms, the running of these effective operators also have anomalous dimensions. When you solve the anomalous dimension renormalization group equation, you end up with things like this. It's easy to see where the word anomalous dimension comes from. If you take the approximation, suppose I took the approximation that alpha strong is a constant. Okay, maybe a lousy approximation, but at weak coupling, alpha does not run very much. Right? That's the nature of it. And so, let's just try it as a crude approximation. In that case, say the first term in the series is alpha, or it doesn't matter. This then becomes a constant, and this is an easy thing to solve, and what you get is MGUT over lambda QCD to order alpha S over pi. Now, since I said that alpha S is small, this looks like a power, and instead of having G being 1 over MGUT squared, the G that's seen at low energies looks like it's corrected by a fractional dimension in MGUT. Okay? And hence this fractional dimension is the anomalous dimension. So that's a crude approximation for small coupling. But for small coupling, this exponent is small. So this seems like only the slightest deviation from the bad news. So instead of getting this result, we'll get some tiny fractional change in the exponent here. Who cares? However, suppose that we have a different type of strongly interacting theory, which also confines and spontaneously breaks electroweak symmetry, all that good stuff. But suppose this constant, and is of order 2 pi, meaning it's a big, strong, this is exactly 2 pi roughly is the point at which perturbation theory no longer works. Okay, perturbation theory is broken down. But this renormalization group structure is reasonably robust. If it's constant, then this thing would be order 1. It would be 2. In that case, this statement here would not be correct. There would be a term that goes like MGUT over lambda QCD to the order 1.
So then it will not be obvious what you're going to get. Okay? You could actually get, one thing you can predict for sure, if you have this kind of sensitivity, it's unlikely to perfectly match. You can still get this being smaller than this, and so this thing wins. You'll end up with hierarchically small epsilons. Okay. But now they may not be so small. They may not be ridiculously small. Okay. So now the game looks open. In fact, if you go back to 3 generations, or n generations, you can have several such operators. You can have several species of baryons, or technibaryons that you mix with, etc. And in general, you will have these epsilons, epsilon I for generation I. And you can have the left-handed guys, or the upright types, or the downright types. Okay, and these epsilons are some sort of fractional powers of a large hierarchy. Generally, be fractional powers of a large hierarchy, so they don't have to be super, super small, but merely hierarchically arranged. And then the mass of fermions in the standard model, if some plot like this plays out, would go like epsilon left I, so for example, let's do uptight. It could be leptons of uptight, or it could be quarks of uptight. Would look like this. Times some order 1 effect of electroweak symmetry, right, like the W mass. Note that this is, note that this is exactly the, so you might say I cheated because I knew where I was headed, but the data is vaguely consistent with this kind of hierarchical structure for the quark sector. Indeed, the leptons look similar. And you might say that then the neutrinos should also be very hierarchical. And since I'm running out of time, I'm not going to tell you what happened. So there's a nice story of the neutrinos, but let me not do it right now. So this is an interesting theory of what could happen if we pursue just single-mindedly this one idea that there is sort of dynamical symmetry breaking at the root of the electroweak hierarchy. Yes?
If atmospheric is very large, how can you separate the gas scale and the lambda Lucid scale?
Oh, yeah, so let me draw this, good, let me draw the following picture, which is next image. What's going on once we've lost asymptotic freedom and the usual, that's the question. What's the rationale for saying that the coupling used to be weak and now it's strong? If it was always strong, what's happening? Here is the normalization group picture. So in some space of couplings, this the way the normalization group always works is you have some space of couplings, and as you evolve in mu, as the renormalization group scale goes down, you flow somewhere in coupling constant space. Okay, this is the executive summary of running couplings and so on. Okay. If a typical phenomenon in normalization group flows, as far as we understand it, even non-perturbatively, is that you can have something special happen. The simplest renormalization group flow, like a river flowing along, is a dead zone where the flow stops. So if I put the leaf here, the leaf moves down the river in some way. If I put the leaf here, it just sits there. That's the notion of a fixed point, a renormalization group fixed point.
if you're close to a fixed point, if you're close to all the beta functions are smooth and so on. If you're close to a fixed point, then you are approximately, you're slow instead of being rapid. So the typical thing is the renormalization group, these double arrows mean the renormalization group as I go down decade by decade in energy, the coupling moves a lot. It's running, it's doing stuff. But when I get near the fixed point, the running slows down. Which means that 10 decades go by in hierarchy. 10 decades go by. And very little has happened. But eventually, I keep going, and then things pick up. And then interesting things can happen. For example, this might be some, now, I've drawn it. This is the strong coupling. This is what happens at weak coupling, but it's also the generic sort of behavior at strong coupling, that this kind of thing can happen. At least at some energy scale, you might end up with a coupling so fierce that bad things happen. All the physical particles get masses. Okay? That's what happens when QCD gets strong. But it's possible that you can spend a lot of time near one of these fixed points and you still have not generated the mass gap, you have not generated the strong interaction scale or the mass of the proton or any of those things. Chiral symmetry breaking is not happening. But eventually you start flowing rapidly, the coupling blows up, the theory blows up, everything ends, and you end up with the end of the flow, if you like. In fact, the fact that you can be near, so you want, what is it like to be near this fixed point? If this is a strongly coupled fixed point, to say you're a fixed point means that no matter what energy you look at, the world looks self-similar to any other energy scale. Okay, this is a place where its physics is scale invariant. Which means there's no scale at which you can say, ah, that's where electroweak symmetry broke, or any other. There's no special scale in the theory. So this is a place which has no preferred mass scales. If you look in the spectrum, you're not going to say, here is a preferred mass scale. And if you're close to it, then that's similar. But if you're close to it, if you're close to it, eventually you will leave this domain where the world looks very scale symmetric, and you'll go somewhere else. And when you go somewhere else, it's entirely possible that you generate a mass scale like the mass of the proton. So the statement is, in order to understand large hierarchies, all you need to understand is you don't need asymptotic freedom. You need asymptotic conformality, or if you need asymptotic scale invariance. Okay. So here is something where I'm at least approximately asymptotically scale invariant. I could even come right out of this. I could be asymptotically approximately scale invariant, which means that very little happens, decade after decade of energy, very little happens. But once I finally escape the dead zone, rapidly the coupling evolves in some way and interesting things happen, okay? Because you're at strong. This is the picture that you'd like to explore. This is, you might say, where's the equation that goes with that? This is the picture above. So there's a lot of sort of tricks for trying to see examples of this type. But let's say there's nothing that you can write out in this case for the story that we want. We can imagine how the story might work. And yet, we lack the tools to directly attack it and say, here is an example, here is something under theoretical control. But we can imagine it. In other words, if you are trying to take the strong dynamics approach, there is since it pertains to experiments, you might say, let's say that the strong picture is innocent until proven guilty, rather than guilty until proven innocent. Usually the standard for theorists is guilty until proven innocent. You have a model? Please show me exactly every detail.
because you can. It's perturbative, you can write the Feynman diagrams, then I'll check everything and see if it makes sense, if it agrees with the data. We are now in such a tight and tough situation, we have to switch to a innocent until proven guilty. We have a plausibility argument for how strong dynamics might work. It's a striking thing that you even see how it works in the standard model where QCD plays the role of Electroweak symmetry. You see it qualitatively, and something like that might be playing out in the real world. We would like to get more understanding of it, and we are taking an innocent until proven guilty approach, which is because we are so poor at being able to do strongly coupled theories. But certainly, we would like to sort of have a better picture. We'd like to flesh out this thing. So I want to give you that. But in terms of maximal rigor, we do not have examples that are relevant to the real world where we can control this. We do have other examples, which are toy examples that one can study, which have exactly this kind of aspect where we have other control models that allow us to control it. But this gives the plot that you can imagine happening. And in that kind of situation, it's the kind of flavor structure that we naturally get. Let's see. Yeah, so I think the next thing that I wanted to do, so I'm going to stop here and take it up next time. The next thing I wanted to do is this question of how do you, so lacking tools to do this, you would like to sort of develop some tools, and one of the great advantages is to try and geometrize the question so you can see with your eyes what we're talking about. At the moment, this thing is so abstract that it's not clear whether you can even wish. You know, let's not even try to write strong dynamics. Let's have a wish list for strong dynamics. But is your wish list self-consistent? By waving my hands like this, it's not obvious. So next time, I just want to point you to this extra dimensional or geometric approach to having a sharp wish list with some self-consistency checks. And this is the best that we can do in a completely realistic setting. And then in toy models, then you can have much greater control using various other tools. Okay, so we'll do that tomorrow. And then hopefully I'll have a little time to talk about the anthropic principle. Any other questions?